Page 5 of Applications of Calculus Kinematics. Remember from last page, we talked about how the integral of the velocity function gives you the displacement if you integrate it over a period of time. Let's talk more in detail about that. There's a relatively difficult to remember but useful procedure to find displacement from a velocity function. The first thing you're going to do is you're going to draw a sign diagram, and the reason why for the velocity function, the reason why is because if you are changing directions while you're moving through the velocity function, it's super important to mark those direction changes, because if you don't, then you're not going to properly calculate the distance traveled. Because like if you're going forward and then backward, then the backwards motion is going to cancel out part of the forward motion, right? And when you want to calculate the distance, you want all the forward motion plus all the backward motion. You don't want them to cancel each other out. You want to add them all up as positive numbers. So that's the challenge here. Okay, so first thing you do is you do a sign diagram, and the reason why is you want to find the direction changes when they happen. Then you're going to integrate v to find s. Okay, you're going to find the s function, including constant of integration. So that's kind of related to the starting point. Then you're going to find, using the s function that you found, you're going to find the beginning displacement point and the ending displacement point, which are obviously two of the most important points to find the total distance traveled. But then you also need to find any position or displacement when the direction change occurred. Okay, and then finally you're going to draw a motion diagram, which is a nice useful diagram which shows each leg of forward and backward direction, and it makes it easy to add them all up. And then finally you're just going to use the motion diagram to calculate the total distance. All right, so it's kind of hard to follow that, but we're going to do a couple problems like that, and then you're going to see that, okay, each one of these steps makes sense, and it's not really that hard to muddle through it, even if you forget the procedure. Under what circumstances can we simply use the integral with the modulus below? So if you look at this, the absolute value function would take any of the negative direction velocities and change them into positive direction, so that when you integrate it, you would always get positive values of displacement. This method works if you're using technology, okay? If you're doing it by hand, you would actually need to figure out when the velocity function was negative and separate it out into like two different integrals. Like you would need this integral, and then you would need this integral, and every time you had a direction change, you would break it up into a separate piece. Okay, draw arrows to show how you go from one quantity to another by differentiation or integration. So like we saw before, when we on the first 3 pages, we saw that if you take the derivative of displacement, you get velocity, and if you take the derivative of velocity, you get acceleration. So we also saw above that when you take the integral of velocity, you get displacement. And so since integration and derivatives are inverse functions, when you take the integral of acceleration, you also get velocity. Okay. Let's do a couple problems. A particle has a velocity function, like so, as it moves in a straight line. The particle is initially 2 centimeters to the right of O. So the initial position is +2. So the velocity, I'm sorry, not the velocity, the displacement at 0 is equal to 2, right? Okay, write a formula for the displacement function. So remember, the displacement function is the integral of the velocity function. So let's do the integral of 1 minus 2t. It would be t minus 2t squared divided by 2 plus c. That's our displacement function. The only thing we need to do to have the complete function is we need to figure out what c is. The way we figure out what c is we use this initial condition. So if we put in t equals 0 and s equals 2, we will find out, let's see, it'll be 0 there minus 0 there plus c equals 2. Oh, so c is equal to 2. Okay. Is c always the starting position? No, we're going to see cases where c is not the starting position. Okay. So the complete formula would be s of t equals t minus t squared plus 2. Okay. All right. Next one. Find the total distance traveled in the first second of motion. Okay. Before we do that, we probably should check number 1 here. Draw a sign diagram. At least we should do that to see if there are any direction changes. So we're going to draw a sign diagram for velocity. And we can see that the velocity function of 1 minus 2t does change direction at least one point. We set it equal to 0 to find out which one. 2t equals 1, t equals 1/2. So it changes direction when t equals 1/2 or 0.5. When you are to the right of t equals 0.5, if you put a big positive number in here, you can see that it would just turn into a big negative number. And then if you put a big negative number in here, you can see that it would become a big positive number, right? If I put negative 100 here, it would be negative 2 times negative 100, it would be positive 200, so it's a big positive number. Okay, so there is our sign diagram, and it tells us that at t equals 0.5, we need to be careful because there's a direction change. It says find the total distance traveled in the first second of motion. Does the direction change occur in the first second of motion? Yes, it does. Okay, so in order to figure out the total distance traveled, we need to know the initial position, we need to know the final position, and we also want to know the position when the direction changed. If we know those 3 positions, then we can use the motion diagram to see what the total distance is going to be. So s of 0 we already know is 2. S of 0.5 we haven't calculated yet. If we put 0.5 in here, if we put 0.5 into the s function, which is here, we would get 0.5 minus, ooh, that's kind of messy. Let's put it in the calculator. So I'm going to put the s function here. The s function is t minus t squared plus 2. So x minus x squared plus 2. And I will look at the table. And so I can see that at s of 1, it's also at 2. What about s of 0.5? How can I see that? I can see that by doing plus 0.5. 2.25. Okay, so now I'm going to draw a motion diagram because I have these 3 positions. The motion diagram is a number line. It's based on a number line with the s values. So the 3 values that I'm looking at here are 2 and 2.5 and 2 again. So it starts out, the object starts out at s of 0 at 2, right? So I'm going to start here. This is t equals 0. And then it's going to go to the right until t equals 0.5. It's going to go to 2.25. So at t equals 0.5, it's turning around at 2.25. And then finally at s of 1, it is reaching 2 again. It's coming back to 2. Okay, so we can see from this drawing that the distance traveled would be 0.25 in this direction and then 0.25 in this direction. So a total distance of 0.5, right? So total distance traveled in the first second of motion is 0.5. C, find the displacement of the particle at the end of 1 second. Oh, so that would be s of 1 equals 2. right? It would be 2. All right? That's it for number 1. Let's go to number 3. The velocity of a moving object is given with this function. If s equals 16 when t equals 0, find the displacement function. Same thing we did up here. We did the integral, right? We're going to do the integral of v, and that'll give us s. So the integral of v would be the integral of 32 plus 4t, which is equal to 32t plus 4t squared over 2 plus c. And then we're just going to set that equal to our initial conditions. The initial conditions was at t equals 0, s equals 16. So if I put 0 in for t, I would get 0 plus c equals 16. So at s of 0, t equals 0, s equals 16, and by doing that I found out that c is equal to 16. So now I'm going to rewrite this function with c equals 16. Okay, so there is my s function with the c complete. Explain why the displacement of the object and its total distance traveled in the interval blah 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 can be represented by the definite integral 0 to t1, 32 plus. So you can see that like the v function is substituted here, the 0 and the t1 are substituted here. Why not use this? What's the problem with using this? Well, it's only a problem if the thing is traveling backwards, in which case it'll give you a negative number, and we want total distance, so it should come out to be a positive number. And the other problem could be that there's a direction change, and we need to make sure that there's no direction change in that interval. So is there a direction change? Let's find out if there's a direction change by setting the velocity equal to 0. Is there a direction change? Is there a moment where the velocity is passing between positive and negative or negative and positive? So it looks like there is a direction change, and it occurs at -8 seconds. Now, is -8 seconds in our domain? No, because the moving object is being observed starting at t equals 0. So t equals -8, and maybe there's direction change, but we're not watching it then. Okay, so that is why the displacement blah 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 can be represented by this integral, because it's never going backwards. To prove that it's never going backwards, let's make a sign diagram for the velocity. At time equals -8, the velocity is 0. At time is to the right of -8, like at 0 or 52 or some other value, it's a positive number. So since the thing is always a positive velocity, that means it's always going to the right. If it's always going to the right, you can use this integral here with no absolute value sign and no negative signs taking care of that. No problem. If it's going to the right and it's never turning around, then of course you can use this very simple integral here. Show that the object is traveling with constant acceleration. Okay, so remember, acceleration is the derivative of velocity. So if we want to know what the acceleration is, we just need to take the derivative of velocity, which would be 32 derivative would be 0. 4t derivative would be positive 4. Okay, so that means the acceleration is positive 4, so it is a constant acceleration. It's always 4. Okay, all right, I think that's it for this page.